Good morning, everybody. Any questions? Okay, so in the previous class, we started a new topic, which is the reduction of multiple systems. And therefore, we're going to continue today on this topic. So what we're going to be doing, we're going to be looking at two different representations of the system, which is the block diagram. And then we're going to introduce a new representation, which is the signal flow. We're going to look at the reduction of the block diagrams. And then with the signal flow, we're going to introduce a rule that is called Mason's rule. And we're going to use that also to get the transfer function between the input and the output. Okay, so let's start with the first one, which is the block diagram. And let's introduce the building blocks of the block diagram. So the elements of block diagram. We have signals, which we represent by these arrows. So we can have the input, we can have the output. And depending on where the arrow is, it will be clear whether it's an input or an output. Another component is the system or subsystem, and we represent it with a rectangle that will have the transfer function inside of it. So this is a system / subsystem. Another element is a pickoff point. And we could have a signal out of S where we can pick multiple branches from it. So this will be out of S, out of S, out of S. Another element that we'll see is the adder. So if we have R1 of S, R2 of S, R3 of S. Now, depending on the sign that these are coming to the adder, they're going to be added or subtracted. So in this case, we're going to have R1 of S minus R2 of S minus R3 of S. I mean, keep in mind, the symbol here is an X, but in reality, it's just an adder or subtractor. And this is the output of this adder. Okay. Let's look at some common topologies. So the first topology that we can see in our block diagram representation is the cascade form. And in this topologies, we're going to have multiple blocks. In cascade. So we can have an input R of S, G1 of S, G2 of S, G3 of S, and this is the output C of S. What is C of S going to equal to? Very good. G1 of S, G2 of S, G3 of S multiplied by R of S. And therefore, we can take all these blocks and reduce them into a single block. This is R of S, C of S, and inside this block is G1 of S multiplied by G2 of S multiplied by G3 of S. What is the assumption that we make when we reduce these multiple blocks into this block? Can we always take two circuits and just take the transfer functions of them and just multiply them if they're cascaded? No. What is the assumption that we make, or the condition that we have to check to make sure is met before we can do this?
Linearity.
What is it?
Is the linearity of the system?
What else?
Cancel?
What is it?
They don't cancel each other, like zeroed out.
More. What else?
Additivity.
You're insisting on linearity? Linearity solves like probably 50% of the world problems. But there's still other solutions. Okay, the assumption that we make is that the adjacent blocks does not act as a load on the previous block. So the assumption is that adjacent system or block does not act as a load on the previous system. What does this mean? Let's look at an example and see what it means. Let's say we have a circuit that looks like this. We have a source, V input, we have R, and we have R. And we have another circuit and this is R over 2, R over 2, R over 2. And this is V input 2. And we have V output here. And we have the output 2 here. So if I look at this circuit, what is the output over the input? Anybody?
Is it R divided by 2 over?
This one, this circuit.
Isn't it R over 2R?
R over 2R. So what is it going to be?
R over 2R is 1/2.
1/2.
Okay. Think about it.
I mean, the voltage is going to be split evenly between this and this. So therefore, this voltage is going to be half the input. Okay. What about the second circuit? What is V output 2 over V input 2?
R divided by 2 over. R divided by 2 plus R divided by 2.
Which is going to equal to what?
I would guess 1/4.
What is it?
Was it 1/4?
No, why is it
I don't
1/4?
know. I was guessing because that one's 1/2. To be honest.
Is it still
1/2, yes. I mean, the same logic applies. This voltage is going to split between this and this. These are equal.
Yeah.
Okay. So then, somebody needed to build a circuit and decided they're going to build a circuit like this. They're going to take the first circuit, V input, R, R, and then take the second circuit, and they decided, okay, well, we learned in control systems, we can we do block diagram reduction, and therefore this is the gain is 1/2, this gain is 1/2. If we cascade them together, then what is the gain going to be? 1/4. Is that the right answer though? No, it is not the right. Is everybody with me? I feel like. So what we're saying is, what we just introduced is we can reduce blocks if they're cascaded next to each other. We can combine them. So if I look at this, I can represent this as a block that looks like this. 1/2 V input, V output. This I can represent it as a block, V input, V output, 1/2. Now if I take these together, somebody is going to say, okay, combine them together, this is 1/2, this is 1/2, then therefore V input over V output 2, this is 2, is going to be 1/4. Make sense? But this is not correct. Why is it not correct?
Because you're reducing, so it'd be 3/4.
Because this system that we added here is going to act as a load on the first system. Does that make sense? And therefore, what we said, the condition that we can combine these is that adjacent system does not act as a load on the previous system. Together? When I add this system, if I take the input and replace this input with this output, this added system is going to act as a load on the previous system. If that is the case, I cannot just combine the transfer function of this multiplied by the transfer function of the second one. And if I look at this new circuit that we built, V output over V output 2 over V input is going to equal to 1/2 multiplied by 1/1.5 multiplied by 1/2. Together? If I take these equivalent, this is an R plus R, it's going to be an R in parallel with R, R over 2. Then this voltage that we calculated is going to be R over 2 over R plus R over 2. But then this voltage is going to be split also among R over 2 and R over 2. So this is the transfer function of it. How do we solve this problem? How do we make it such that the transfer function between this input and this output is indeed 1/2 multiplied by 1/2?
You use a Hopper.
Excellent. No. Too early in the morning for that. So the solution to that to solve the loading problem, we use buffer. And therefore, we can combine the circuits like this. This is an R, this is an R, and then I'm going to take R over 2, R over 2, and this is V output 2. In this case, what is the equivalent between V input and V output? It's going to be 1/2 multiplied by 1/2 and this is the output 2. Is that clear? And therefore, I can cascade these and add them together into one block that is equal to 1/4. And again, why did I write this like this and this like this?
No reason.
For no reason. Very good. Okay. So what does this buffer do?
Prevents the loading.
Yes. How does it prevent the loading? The input impedance of the buffer is infinity. So therefore, when I added it to this circuit, it does not see the load that is connected after it. And the output impedance of it is 0. And therefore, this circuit, when it looks back, the output impedance of it is 0. And therefore, whatever the voltage is going to look like an ideal source. Okay, so keep that in mind, that we can cascade 2 blocks and reduce them, granted that the reduction or the combining, one of the block is not loading, is not a load on the second block. Okay. Another form that we will see is the parallel form. And this will look something like this. We can have a G1, G2, and G3. And we can add them all together, subtract them, or have any different signs. So it could be positive or negative, positive or negative. And if I have an R, what is the output C of S going to equal to? What goes inside these brackets?
G1 plus or minus G2 plus or minus G3.
Yes, plus or minus G1, plus or minus G2, plus or minus G3. And therefore, we can reduce all these blocks into a single block. That's going to be plus or minus G1, plus or minus G2, plus or minus G3. This is R, this is C. Is that clear? Everybody? Okay. The next form is the
Sorry,
Go
the
ahead.
R is R of S, not R as in the resistor, correct?
R of S.
Okay.
In general, R of S, C of S.
Okay.
Yeah. And the same thing with G1, G2, G3. G1 of S, G2 of S, G3 of S. Everything is a function of S. Okay. The second form that we will see is the another form that we will see is the feedback form. And in this form, we're going to have an input R of S. We're going to have a forward gain G of S. We have the output C of S, and then we have a feedback H of S. And this feedback either subtracted or added to give us this circuit or this block diagrams. What is this C of S represent? What does H of S represent?
Transfer function?
A transfer function. That represent what? What is it?
Is it V on over V on?
Like when is it we're gonna be seeing lots of this form in the class, but lots of times it's gonna be just a unity. It's gonna just look like a 1. Just one C of S fed back directly to the input. But when is it we're gonna have H of S, and when is it gonna be a 1? What does H of S represent?
Output over input?
Yes. What else? Okay, so this is what it represents, and keep it in mind. If the nature of the output is different than that of the input, then I need to somehow translate from that nature to this nature. What is an example of that? If I'm applying a voltage here, and I'm trying to set the temperature in the room, what is the output going to be? Temperature. What is the input that I'm applying? A voltage. How I'm going to subtract a voltage? I'm going to take measure the temperature, and I'm going to subtract it from the input. How I'm going to subtract temperature from the input? I can't, can I? What do I need? I need a sensor to measure the temperature. What is that sensor going to do? It's going to take the temperature and it's going to give me a voltage that corresponds to that temperature. What is this transfer function going to represent? The transfer function of that sensor. Does that make sense? So anytime I see H of S is here, it tells me that the nature of this input is different than the nature of that output. And this sensor is translating this nature to this nature. Is that clear, everybody? Okay. So again, this H of S could be translating the output, which is, for instance, a temperature in Fahrenheit, to a voltage. Now, one more thing I want to mention about this H of S. Usually, also, when we see H of S in this block diagram representation, it is either going to be a constant, is going to be either a 1 or a constant. What does it mean when it is a 1 or a constant? What does it mean when it's a constant? What is it? No. This is what it means, and I want everybody to know this and keep it in mind. It means this sensor that I'm using in the feedback is very, very fast, that there is no dynamics in it. It's almost instantaneous. Does that make sense? So if I'm running a system here that heats the room, this system takes minutes or like tens of minutes to heat the room. The sensor can measure the temperature in 1 second. How am I going to represent this sensor? Just as a constant, because it's so much faster than the system here that I'm going to just assume it is almost instantaneous. Is that clear? Okay. So please keep that in mind. Go ahead.
Is that in every case there's a feedback form, or just in this particular case?
In most of the cases. Most of the cases, when there's a feedback, it means I'm measuring the output, which means I'm using a sensor. So if I'm building a system where I have to measure the output, most likely I cannot control that system itself, but I can control the sensor that I'm going to use to measure the output. If I were to select a sensor to measure the output, I'm going to select the fastest sensor that is possible. And therefore, this sensor is going to be much, much faster than this, that I can just represent it by a constant. Make sense? Okay. And we'll see, hopefully, this again when we look at the response of the system. Okay, so in this system, in this feedback form, we define this signal as an error signal, because this signal is R of S minus C of S. Is the input minus the output, and therefore it represents the error. E is equal to R minus H of S multiplied by C of S. And this is of S. But I'm going to take all of S out just to make it more clear. So this is R minus H multiplied by C. Now at the same time, what is C equal to? G multiplied by E. If I look here, C of S is equal to G of S multiplied by E of S. And therefore, I can write this as E of S is equal to C divided by G. So I'm going to go to the previous equation and substitute for E. I'm going to have C divided by G equal to R minus H multiplied by C. I'm going to move the HC to the other side. I'm going to get C divided by G plus H multiplied by C equal to R. I'm going to take a C as a common factor. I'm going to get 1 over G plus H equal to R. I can write this as C G 1 plus G multiplied by H equal to R. And therefore, I can divide C by R. And this is going to equal to G divided by 1 plus G multiplied by H. Together? So this is the equivalent of this feedback form. And keep in mind, if I have a negative sign here, which I had here, so the error is E minus H multiplied by C. What is the sign here? A positive sign. So if it is negative there, it's going to be a positive here. If this was plus, what is it going to be here? A negative. Make sense? Following the same development. Most of the time, we're going to see this as negative sign. So therefore, it's going to be G divided by 1 plus G multiplied by H. Okay. Now one thing we're going to define here, this G multiplied by H, we're going to call it the loop gain. Why is it the loop gain? G multiplied by H. G multiplied by H is the loop gain. Because if I go around the loop, what is the gain that I'm going to experience? G multiplied by H. So therefore, G multiplied by H is called the loop gain. Okay. Is that clear, everybody? Now imagine everybody probably going to know this by heart, so we're going to be seeing it and using it throughout. Okay, another simplification that we can have if I have an R another signal x. So C here is equal to G multiplied by R minus X, which is equal to GR minus GX. I can change the representation, this representation, into the following. I can take R multiplied by G is another G, and this is an X. What is C gonna equal to here?
GR minus GX.
Same thing. Okay. Another simplifications that we can do is I can have, if I have an R that goes through a G, this is going to be equivalent. So what is it I've done here? I've taken this G and I moved it back. Since both of these are added multiplied by G, I can just multiply the G before I added them. So I multiply G here, multiply G here. Make sense? Intuitive? Now what if I have a G like this, and I want to move this G till after the adder? What do I have to do? So I'm saying, what if I want to change this representation to the following? This is a G and this is a C. What should go in here? Let's take the top one. What should go in the top one? What should go here? R. Any objection to R? R.
Thanks, buddy.
What should go here?
X divided by G.
X divided by G. Excellent. Everybody agrees? X divided by G. So therefore, I can add a block here that is 1 over G, and this is an X. Both of these are equivalent. X is going to get divided by G, but then it's going to get multiplied by G. It's going to give me an X. R was originally multiplied by G. Now it's going to get multiplied by G. Both of these have the same output. Is that clear? Everybody agrees? Okay. Another simplification we can do is if I have R this is R multiplied by G, R, R. If I want to move G, so it multiplies R directly. This is going to be R multiplied by G. This is 1 over G, and therefore it's an R. 1 over G, and this is an R. Together? Now we will see, taking these pieces alone is not clear why we're doing this, but it might be having this form instead of this form when we do the block diagram reduction will make the representation easier to simplify. Okay, Another thing we can do, if I have an R, I have a G, R multiplied by G, multiplied by G, R multiplied by G. This is the same, this is equivalent. This is equivalent to R and having a G here, having a G here, having a G here. Agree, everybody? Okay. Let's take an example. Okay. So to apply all this, let's look at this block diagram and try to reduce it into a single block. And what we have is G1. We have an R. This is G3. And we have 3 feedback loops. This is the first loop, H1. Another loop, H2. And a third loop, H3. What goes inside this G1, G2, and G3? What is G1, G2, and G3, H1, H? What are these? What do they represent?
Components of the system,
More specifically,
like resistors, best items, I guess.
more specifically, or more accurately, what do these represent? No. No. What do these blocks represent?
Operations you're performing on the system.
Keep going till I tell you. Anybody? Where's lecture 3? Where's lecture 3? Lecture 4. There we go. What did these blocks represent? You guys, do you remember seeing this? What is this block, this block, this block? We model the system and we carry up with these transfer functions. Make sense? So if I'm trying to do block diagram reduction, I'm going to call this, for instance, G1, G2, G3, and this is H1. So what's inside G1? 1 over R plus SL that's multiplied by LA. What is inside of G3? 1 over whatever this expression is. Together? Is that clear, everybody? So keep that in mind. So when we are doing this, what are these? G1, G2, G3? It is whatever transfer function we came up when we model the system. This is how the model of the system is. Inside of here is the transfer functions that we use when we model the system.
That come from like resistors and inductors and capacitors.
Whatever circuit, I mean, could be mechanical, electrical, whatever the system is.
Okay.
Make sense?
Yeah.
But it's a transfer function. Transfer function, function of S. That's why we call it G1 of S, G2 of S, G3 of S. Okay. How do we reduce this? How do we simplify this? Louder. We can take G2 and G3 in cascade, and then we can replace them with one block. So we can combine these two. What else we can do?
Add H1, H2.
These, H1, H2, and H3. Excellent. We can combine all these together. And then what do we get when we do that? When we combine these, what is the form going to look like? The feedback form. The feedback form. Okay, so let's do that. So we can combine G2 and G3. And then we're going to have G1. We're going to have an R. And we combine all the feedback loops. See what I did here? I have a minus sign to H1, minus sign, positive sign to H2, minus sign to H3. So I'm going to keep a minus sign, H1 minus sign, H3 minus sign, which is consistent. H2 is positive, so I use negative sign here. Make sense? So this negative sign, if I multiply it, is going to be negative H1 plus H2 minus H3, which is what we have here. Okay, so what do we do next? We can take this loop, and this is a feedback loop. What is the equivalent of this going to equal to? So we have R, this is G1. Can anybody read me, like if you took the notes, what the equivalent of all this is going to be? It's going to be G over 1 plus G multiplied by H. So whatever it is there. So it's going to be G, which is G2, G3, divided by 1 plus G2, G3 multiplied by H, which is H1 minus H2 plus H3. Agree, everybody? What do we do next? You can just combine these two blocks. G1, G2, G3 over 1 plus G2, G3, H1 minus H2 plus H3. And this is R, and this is C. Is that clear, everybody? Okay, let's do another example. You're going to have an R, G1, okay. Okay, so we're going to reduce this block diagram representation. Who has ideas? Oh, this V1, this is V2, this is V3.
Can we go ahead and do the feedback form?
This one?
Yeah, you said.
Yes, we can reduce this using the feedback form. Excellent. What else? How do we reduce the blocks on the left side? How about if we did not have this? How do we reduce it if we did not have that? We have a feedback form here. We take the equivalent. There's another feedback. Make sense? But we cannot do that. Can we do that in this form? No, because we have this pickup. This voltage is picked up from here. And if we do that, we're going to lose this point. So what do we have to do? Does everybody see what the problem is? Any ideas?
Maybe you can start on the left and to start with G1 and H1 and try maybe G1 over 1 plus G1 H1 maybe.
We cannot because this block is not like in a form. We can just use it. Can anybody tell me what the problem is?
A circuit.
What is the problem with reducing this? What is it?
Which part of that? Is it all of it or just the?
Anyway, it's like, why is nobody giving me ideas?
It's all
I just want to make sure the part that should be you're focusing on is the part you're focusing on, and it's not something else. What is the challenge with this circuit?
Ensuring that the output going to the next block is
V3?
equivalent.
This one?
Right.
Yes.
For the-
This is the problem with this circuit. Again, if we did not have this one, we can easily do a feedback and then a feedback, combine them all together. But we have this signal, I'm taking this error signal and I'm using it and I'm feeding it forward. How can I solve this issue or problem?
Get rid of B3.
Get rid of V3. Excellent. How do I get rid of V3? I can move it forward. How? I can take it from here, and instead of taking it from here, I can move it and take it from here.
And then divide by,
How? And then what do I have to do?
times by 1 over G2.
I have to divide it by G2. Make sense? So that's the trick in this circuit. Okay. So we're gonna take this. And what we're gonna do, we're gonna get rid of G2. Sorry, we're gonna get rid of the pickup line. G2 will stay here. Rather than picking up before G2, I'm gonna pick the signal after G2. So I'm gonna pick it up from here. And now I'm gonna divide by G2. Everybody agrees? So all what we've done, we moved this point. Instead of being picked before G2, I'm picking it after G2. Since this signal now is multiplied by G2, I need to divide by G2 to get the original signal. Okay. What do I do next? I can take these as feedback form. I can take these as feedback form. I can combine these together. And therefore, I can reduce this. So here we have a 1 plus 1 over G2. I have G3 over 1 plus G3 multiplied by H3. Is it clear where this one coming from? Where is it? From this line here. Okay. this is going to be G2 over 1 plus G2 multiplied by H2 Okay, so then we have a feedback loop. That we can reduce. It's going to be G1, G2 over 1 plus G2, H2 over 1 plus H1 multiplied by G1, G2 over 1 plus G2, H2. Can write this as G2 plus 1 divided by G2 multiplied by G3 divided by 1 plus G3 H3. And then we can reduce them all. It's going to be G1, G2 divided by 1 plus G2, H2 plus H1, G1, G2 multiplied by G2 plus 1 divided by G2 multiplied by G3 over 1 plus G3 H3. Is that clear? Any questions? Now, in general, this simplification is not unique. So there might be other ways of reducing the block diagram, but usually there is one way that is simpler than other ways. Make sense? Okay. Okay, so what is to summarize, when we use a circuit, a block diagram like this, what is it we're trying to do? We're trying to have it in any of the standard forms that we have. And the most useful form is the feedback form. So we're trying to reduce it so it is in a standard feedback form. If we have pickup lines, we have to get rid of them. We have to move them so it is in a standard form. Make sense, everybody? Okay. So this is the first way of taking multiple blocks and reducing them. So what do we do when we get to this point? We can substitute for the transfer function in each one of these and calculate the overall transfer function. Make sense? So this will give me the relationship between the input and the output. Now the second form that we're going to look at, so we looked at the block diagram representation. The second form is the signal flow. So the second method of representing a system is using signal flow. So this is an alternative representation to block diagrams. And the components of the signal flows we have systems and signals. And systems are represented by branches, and signals are represented by nodes. So we can have a branch that looks like this. This is a system. And we can have a node that looks like this, which is a signal. Nodes and branches. Okay. Now, one advantage of the signal flow representation is that we can use Mason's rule or formula to get the equivalent transfer function. So the Mason's formula, which we will be introducing, will help us calculate the equivalent transfer function, and it is methodical, so you can just apply it, and it will help you get the transfer function. Okay, so let's look at how we go from a transfer function to a signal flow representation. So let's look at some examples. So let's look at the feedback form. So if I have this feedback form, this is in a block diagram representation. I can represent it with a signal flow as follows. We're going to have an R, is a 1, this is G, and this is 1, and then I have a feedback negative H. And the signal here is E. And these circles are open. Now I have them closed. Okay. So this is the signal flow representation equivalent of the block diagram, the feedback form. R, error, signal, G1, negative H, and then the output. So each one of these branches represent a system or subsystem, and the direction tells you how the signal is flowing. Is that clear, everybody? Now, what is this error signal here equal to? If you look at it here, what does it look like it's equal to?
R plus H minus G1.
Excellent. It is R minus H times C. The error signal here is equal to R minus H multiplied by C. I mean, don't look at it and look, oh, I mean, if we are not interested in the signal flow, I can look at this and say, oh, E is equal to R. There is a 1 here. But what this E means, after this node, this node is going to equal to R minus H multiplied by C. And this E corresponds to the value here. Is that clear? Everybody? Yes or no? Okay. Let's look at another example. So this is A, B. If I have an R and a block G1, a block G2, a block G3, and this is C. I can convert this to a signal flow as follows. This is a branch, a branch, a branch. This is G1, this is G2, and this is G3, and this is C. And if I have, for instance, a voltage, a signal here that is V2, then I can write 2, this is V2. This is an R. Okay. Let's do another example. G1, G2, and G3. V1, V2, and V3. So I'm going to have an R. And G2, G1, and G3. And the first one is added. I have a line with 1. The second one is added plus 1. And the third one is subtracted. So we have a negative 1. And this is C, and this is a 1. Does that make sense? 3 branches, G1, G2, G3. Since G3, the signal from G3 is subtracted, we have a negative 1 that will multiply G3. Okay. Okay, let's take the example that we've done before and convert it to a signal flow. So let's go back. Okay, so this is the example we just did. We're going to convert it to a signal flow. So we're going to start with R. We're going to have V1, and this is going to be multiplied by G1. Then we're going to have G2. This is G3. And we have a signal that is going to the input here. Is a 1. And we have a signal at the output of G2 that has H1 and then -1. And then we have a signal that is from the output, the H3. And -1. Okay. So we have V1, V2, and we have V1, V2, V3. Let's call this V4. This is V5. And let's have this as V6. And this as V8. And this as V7. So we have V1. This is V2. This is V3. This is V5. V8, V6, and we are missing 1. This is H2, and this is V7. Is that clear, everybody? So V1, V2, V3, V4, V5, V6, V7, V8, V1, V2, V3, where is V4? We have V4, V5, V6, V7, and V8. Okay. Now what we're going to look at next is how we can take this signal flow and do some simplification to it before we apply the Mason's rule. So one of the simplifications that we can do is that if we have a node that have a single flow in and a single flow out, we can remove it. So what that means, if I have -1 here, and I have H3 here, I can replace this with just -H3. I have a node that has a single flow in, a single flow out. I can just combine them and remove that node, and I have -H3. If I have a node that has G1 and a 1 here, this is the same as just having G1. Together? Okay, we'll stop here.